and bases. We're off to 16, second to last chapter of the year. That's a good deal. Bases here today. So acids were first recognized by their sour taste. You guys used an acid the other day when you did your titration there. Actually, there was that acid there, which was acetic acid. Acetic acid is really the main component of vinegar. It's a weak acid. There's acids that are citric acid as well, in like lemons and fruits and those type of things. Bases, on the other hand, are recognized by their bitter taste. Don't taste any acid or bases. You shouldn't, by the way. They also feel very slippery. If you ever get a base on your hand, it really feels almost like you got a layer of something over it. I know, because somebody handed me a base in my hand once when I was teaching, and you got this really nice layer of like slippery feeling on it. A lot of soaps, a lot of drain cleaners and stuff like that are bases. You could actually go buy like straight sodium hydroxide there at Home Depot to unclog your drain if you need. They are also sometimes referred to being in a sort of a basic condition as being alkaline. And alkaline really does refer to being basic. And if you think about kind of our first two groups there on the periodic table, group 1 and group 2, thus there are alkali metals. And that's our alkaline earth metals. And really, those guys in group 1 and group 2, along with hydroxide, really make up a vast majority of a lot of strong bases that we have in nature, like sodium hydroxide, potassium hydroxide, calcium hydroxide. Now, sort of the early sort of definition of acid and bases really came out with a guy named Arrhenius. He did a lot of work with electrolytes. We talked about electrolytes. Electrolytes are things that when they go into water will produce ions. So they'll break up and produce ions, also can conduct electricity. If you remember, there's really were kind of two types of electrolytes. There was a strong electrolyte, which basically when it goes into solution, 100% breaks apart into ions. And there was also sort of weak electrolytes, if you remember, and weak electrolytes are guys that when they do go into water, they mainly stay together, but will produce a little bit of free ions. So they are still able to sort of break apart a little bit, but they do mainly stay together. We also, if you remember, sort of differences in arrows. Strong electrolytes usually have a one-way arrow, and it is those weak electrolytes that usually have the two-way arrows, kind of the forward and reverse direction. Acids and even bases also basically fall into those categories. Strong acids or strong bases or strong electrolytes, when they go into solution, they 100% break apart into ions. Weak acids and weak bases, when they go into solution, will mainly stay together, but will still be able to produce a little bit of ions, which is why they're still really considered acids or bases. Really, an acid is defined as something that is able to produce a hydrogen ion, which is the H+ ion in solution. And really what that means is it is able to, if you looked at sort of the beaker, produce free H+ ions basically floating around in the solution, not connected to anything else, just kind of floating around in the solution. And that's really what makes something an acid. A base, on the other hand, is something that can create hydroxide ions. And in solution, we're talking about free hydroxide ions. So again, we got basically free floating OH- in solution. As we'll talk about in this chapter, really the difference in the concentration of either H+ or OH- in a solution will determine whether or not something is sort of acidic or basic. So if you have more of the free H+ floating around, it's going to be more acidic. If you have more of the OH- floating around, it is going to be basic. And by the way, H+ and OH- make water. Yes. So it's basically what's happening. What happens with water just by itself, you got basically those guys kind of floating around as water actually reacts with itself. One important aspect of acid and base chemistry is this H+. H plus and pretty much H3O plus, which is the hydronium ion, are essentially equal to each other. So anywhere in formulas, anywhere in sort of equations, you can sort of interchangeably use H plus or H3O plus, which is the hydronium ion. I personally use H plus a lot. Books and stuff tend to use H3O plus a lot. So they're basically equivalent to each other. They're really sort of the acid version of the solution. In addition, this is again the hydronium ion is what is sometimes referred to. And this is obviously the hydrogen ion. H plus is also sometimes referred to as a proton as well. So you'll sometimes see people refer to H plus as a proton, and that is because hydrogen has a proton, an electron, no neutrons. So in order for it to become positively charged, it had to lose an electron, which leaves it just a proton at that point. So it's sometimes referred to as just a proton as well. So again, anywhere, I put in a formula H plus, you can pretty safely put H3O plus, and it really is going to be the same thing. This is an example of hydrogen chloride gas. If we put hydrogen chloride gas, kind of bubble it through water, that is how we kind of make hydrochloric acid, which is HCl. It is a strong electrolyte. It is able to produce H plus in solution, which makes it an acid. Sodium hydroxide, if you dissolve it in water, is able to produce hydroxide, which is what makes it a base. Remember that we did talk about naming of acids, so it's important to remember how to name acids. The quick Cliff Note version of acid nomenclature, right, is it all involves oxygen. And if there is no oxygen involved in the formula, the acid name starts with hydro something ic acid. It's like we have here, our HCl would be hydrochloric acid for the Cl that's there. Remember that if your acid does contain oxygen, it will contain one of those probably polyatomic ions that end in either ate or ite. And if your acid guy ends in ate, the acid name is something ic acid, like HNO3. NO3 is nitrate, right? So this is nitric acid. And if your polyatomic ion there ends in ite, your acid would be something OUS acid. So we'll just take his partner there, HNO2. That is nitrite. That would be nitrous acid, right? So it's important to obviously to know the names of the acids, and when you see a formula, recognize it and be able to name it. Any questions on that? That's what we talked about, I think, when we did naming back, whatever chapter that happened to be. Also, we talked about that typically acids are usually always written with the aqueous symbol next to them, right? And that is because that is pretty much what an acid is. It needs to be able to produce H plus and in a solution, so it has to be in a solution which would have aqueous. That is why this guy in the gas phase is called hydrogen chloride. Yeah, so in the gas phase it would be hydrogen chloride. In the aqueous phase it will allow the H plus ions to go away and float around in the solution. Also, all cations, right, for acids are H plus, right? So H plus is always the positive guy for an acid. Any questions on that there? Now, it was a good sort of introduction to acids, the Arrhenius sort of definition, but he did do a lot of work with really just the bases that contain hydroxide. Not all bases do contain hydroxide. A lot of the strong bases from group 1 to group 2, pretty much you go from group 1, like lithium, sodium, potassium, hang right there at calcium, and come down to strontium and barium with hydroxide. Those are typically your strong bases, but not all bases will have to actually have hydroxide in the formula. Something like ammonia is actually an example of a weak base. And something like ammonia, when it goes into water, the ammonia will actually accept NH plus from the water. The result of that is you will make NH4 plus and OH minus. So something like this, ammonia is still considered a base because it can react with water to produce hydroxide. It is a much weaker base than, say, something like sodium hydroxide, which frankly just needs to go for a swim, and it's going to 100% break apart into the sodium ion and the hydroxide ion. So the difference here is 100% in solution. You know, you're going to have that guy there, which is going to produce a lot of hydroxide really quickly and easily, and thus is going to be a much stronger base than ammonia that needs to go and sort of find some water, do a little bit of a reaction to produce hydroxide. Again, ammonia being a weak base would be a weak electrolyte, so we do see the two-headed arrows typically with it, and sodium hydroxide is a one-way arrow as well. Now, when we look at something like an acid, you can look at something which is sometimes referred to as HA, which is a generic sort of term for an acid. This is what is sometimes referred to as being a monoprotic acid. And a monoprotic acid is an acid that basically has the ability to give away basically one hydrogen. So in a real life example of this guy would be something like hydrochloric acid. You could also have a generic formula for an acid that's H2A, and that is what is sometimes referred to as a diprotic acid. And that obviously has two hydrogens that it's able to give away. A real life example of that would be something like sulfuric acid. And you could also have something like H3A, which is sometimes referred to as a triprotic acid. It has basically three hydrogens that it could give away. It would be H3PO4, phosphoric acid is an example of that. In each of these cases, as I mentioned before, the cation there in each of the cases is H plus. But it is actually the negative guy, or the charge on the negative guy, that does change. In a monoprotic acid, the anion has a -1 charge, like chloride. In a diprotic acid, to balance it out, it has a -2 charge, which is why there's two hydrogens, like sulfate is a -2. And for, say, a triprotic, because there's three hydrogens, the -A actually has a -3 charge, like phosphate does in this particular case. So sometimes in acid-base sort of reactions in chemistry, they'll just kind of use these generic sort of formulas to represent an acid. You can relate it to any real acid if you want, but sometimes that's commonly used. By the way, when we talk about something like sulfuric acid, for example, sometimes people do think that, you know, both hydrogens basically just sort of drop off all at once. It actually does come off in a stepwise fashion. What first happens is the sulfuric acid will essentially lose one hydrogen and be left with HSO4 minus. And then the second step that actually happens is the HSO4 minus will lose the second hydrogen, and you'll get sulfate here. So in a diprotic acid or a triprotic acid, even though they technically can like drop off two hydrogens or three hydrogens, they do actually come off one at a time. And it actually gets progressively harder to remove each hydrogen after you remove the first one. The first one, after you remove it, you can see you become something that's negative, and now you're trying to draw out something else that's positive. So it's very much harder to do so, and even harder in, say, a phosphoric acid situation to try to remove the third hydrogen. a majority of all the hydrogen basically comes off in that very first step. Now, sometimes when we think about it in classes like this and other classes, we think about sulfuric acid as, it just loses 2 hydrogens, and you could get that by adding these 2 steps together. Anything that's on opposite sides of the arrow that are the same would cancel, and this gives us sort of our overall reaction that we sort of oftentimes think about with sulfuric acid, that it does drop those 2 hydrogens and make sulfate. But again, it is sort of a step-by-step sort of procedure as to how they actually come off. Any questions on that there? Now, by the way, while we're talking about that here, I'll just go here. The difference between, say, H3O plus and H plus, and why they are sort of interchangeable, is if you could take an acid like hydrochloric acid and you can show really the dissociation of it or the ionization of it when it goes into water, how it breaks apart by reacting it with water in this reaction. And in this case, the H plus is actually going to go over to the water. And the result is you will make H3O plus and Cl minus in this reaction. And this is basically just showing really hydrochloric acid in a solution is really what it is as it's breaking apart. You could also equivalently show the exact same reaction by just simply showing the H plus coming off and the Cl minus. So these 2 reactions basically show what happens with hydrochloric acid in a water environment. One includes the water in the reaction, and when you include the water in the reaction, you produce H3O plus. When you don't include the water, which is perfectly fine to do with an acid, if you're not showing really a reaction of the acid with anything else other than sort of being in water, you will get the H plus. So that's why, again, those things are used interchangeably in acid-base chemistry, because oftentimes they do barely represent kind of the same thing. Any questions on that there? Okay. So getting back to our definition of an acid and a base, really the probably most common definition of an acid and base that most people follow is what is referred to as the Bronsted Lowry definition of an acid and base. And in general, a Bronsted Lowry acid is something that is a proton donor, which means it is something that gives away an H plus, and a Bronsted Lowry base is a proton acceptor, which means that it is obviously something that accepts an H plus. Now, it is important to remember that it is not just an H, but the plus comes along for the ride. And what happens when you gain something like an H plus, you become one more positive. So you become one, when you gain an H plus, you become one more positive. And when you lose an H plus, you now have more negatives and positives. You become one more negative. And that's really important. We're going to talk about sort of a relationship between acid and bases and what they produce on the other side. And sometimes people get focused on just the hydrogen part and forget about the plus part. It does have an effect on the overall charge of what happens. To illustrate this, we could actually look at either of the 2 reactions we just talked about. We'll take a look at the ammonia reaction here. When we look at the ammonia reaction with water, in this case, what is happening is the water is going to donate the H plus over to the ammonia. In this definition, the water would be our acid. And because the NH3 is accepting the H plus, it would be our base. So that's the Bronsted Lowry definition. The result of that is, as we saw earlier, we will make NH4 plus and OH minus. The sort of consequence of the Bronsted Lowry definition is the acid and base that are found on the left-hand side of the equation will actually have partners on the right-hand side of the equation that they are related to. So in this case, the NH3 is related to the NH4 plus. And since that's a base on the other side, this is what is referred to as being is conjugate acid. And the other relationship is found with the other two guys. On the left-hand side, the water is now related to the hydroxide on this side. The water is the acid. On the right-hand side, this would be what is referred to as the conjugate base. So what happens as a result of the Bronsted Lowry definition is we create these pairs of acids and its partner, which is the conjugate base, and a base and its partner, which is the conjugate acid. Regular acid and bases are always found on the left-hand side of the arrow. Conjugate partners are found on the right-hand side of the arrow in most situations. The only difference is this guy right here, which is the H plus. So the only difference that there can be between a conjugate acid and a conjugate, a base and a conjugate acid, or an acid and a conjugate base, is just one H plus. As we go from the base to the conjugate acid, it has one more H plus because it gained it. And as we go from the acid to the conjugate base, it has one less H plus than it started with because it donated it in this particular case. Any questions on that there? So here's that generic sort of reaction. Here our generic acid loses its proton and makes its conjugate base on the other side. And again, here water, way overshot it there. Water there makes this conjugate acid on the other side there by accepting it. By the way, we also saw earlier this reaction, which was the HCl and the water, right? Making our H3O plus and our Cl minus in this case. In this reaction, it is the water that is accepting the H plus. So in this case, the water is acting as the base. The hydrochloric acid is acting as the acid. That means that the conjugate base would be our Cl minus, and our conjugate acid would be our H3O plus in this case. What we just saw with water in both of those reactions is, in the first reaction, water was acting as a acid, right? In this reaction that we just looked at, as I keep writing lines apparently on the paper there, let's try that again. There we go. And this reaction, water is acting as a base. And there are substances like water that can, in certain cases, act as an acid, and in other cases, act as a base. Those are what are referred to as being amphoteric. So an amphoteric substance is a substance that can act as either an acid or a base, and water is a prime example of that. In certain situations, it acts as an acid. In certain situations, it acts as a base, which is why when water reacts with itself, as we'll talk about, one acts as an acid, one acts as a base. It works really well, for water in that case. So the importance of our conjugate acid-base pairs is, again, it can only be a difference of one H plus. If there's a difference of more than one H plus, they are not related to each other. That is the only difference that you can have in that situation. That is why if we think about the sort of sulfuric acid that we did a second ago with those kind of stepwise reactions, the relationship is, this is an acid, and this guy here would be a conjugate base of each other, as the only difference between those two is one H plus. This guy here and sulfate here would also be a conjugate acid base pair because the only difference is one H plus. Sometimes people go, well, what about like going from here to here? those two guys. Obviously, they are related to each other, but they would not be an acid conjugate base pair because the difference there is 2 H pluses, so too many. And the reason for that is it again comes off one at a time. So those guys would not be pairs going sort of diagonal there because it is a difference of more than 1 H plus. Even though they are technically related to each other, they come from the same acid, but they technically aren't the definition of an acid conjugate base pair that you would expect from Bronsted Lowry. Any questions on that there? Okay. All right, there's our formation of our H3O plus from our HCl. All right, so while we look at one here, so for each of these combinations, decide, does it represent a conjugate acid base pair in each of these cases? Okay, let's take a look, and really the decision is pretty much this: is the difference 1H plus? So that's what you're looking for. So you could do it a couple different ways. You could rewrite them both if you want, and you could either add an H plus to the guy to the right, or you could just take away an H plus to the guy to the left. So if I take away an H plus, I'm gonna get rid of the H, and when I get rid of the plus, I become one more negative. So those two match. So the only difference there is 1H plus in this particular case. If I look at the next two, HCl, ClO minus, if I get rid of the H and the plus, makes me one more negative. They do not match because this guy has a oxygen. So these guys would not be pairs because there is greater than just an H plus difference. So there's more than an H plus difference, which means they would not be pairs. If I look at this guy here, I'm going to get rid of an H, which gets rid of one of those. And once again, when I get rid of the positive, I become one more negative. I'm already at -1, so that makes that -2, and now those two match. So those guys would be a pair. And lastly, if I take the HNO3 and the NO3 minus, get rid of the H, I was neutral, so I'll become one more negative, so they match. So that would be it as well. So it looks like 1, 3, and 4 are winners here. 2 is the only non-Bronsted Lowry, basically pairs here. By the way, I knew the acid is typically the one in a pair that has the more hydrogen. So the acid is typically the guy in a pair like this that would have the more hydrogens. Any questions on that one there? All right, so then for these ones here, for each of these, write the conjugate base. Starting with each of these guys, what would their conjugate base be? So in this situation, once again, we should know that either we want to kind of put on the H plus or take off the H plus. Thinking about what we learned earlier can be helpful in this situation. We know if we have an acid, we have a base on one side of the equation. On the other side, we have the conjugate acid and the conjugate base. The relationship is the acid is related to the conjugate base, and the base is related to the conjugate acid. Excuse me. In this particular case, we are looking for the conjugate base, which means we're really looking to end over here, which means if we follow it backwards, that means that each of these things that we're starting with here are acids. And really all we need to know is the definition of the Bronsted acid, which is it is something that will donate the H plus. So that is how we know we really should just take the H and the plus off of each of these things. So if we do that for the first one, get rid of the H, we're left with HS. We have no charge, but we then would become one more negative as we lost the positive charge. Starting with this guy here, we would take off the H. That would leave us an S. It already has a negative charge, so it would also become one more negative, and that would be S2 minus. In this case, we would take off one of the H's there. And once again, it is neutral, which means it will become one more negative. And lastly here, we would take an H off of here. Gets us HSO3. Once again, it was neutral, so taking off the positive charge there will turn it into a negative. So if you understand the relationship between the acid and the conjugate base and the base and the conjugate acid, sometimes on these type of problems, you want to think backwards to determine what you're looking at. And then you really could just use the basic Bronsted Lowry definition. Acid would donate, base would accept it. Because much like this problem here, sometimes they won't tell you, hey, these are acids or these are bases. So you could kind of use that sort of backwards thinking there to figure out what they are. Any question on any of those there? Now, when you do have something that is amphoteric, say like this guy, why don't you write the conjugate acid for it? And why don't you also do the conjugate base for it as well? So starting with bicarbonate in both cases. Okay, so in this situation, we'll start with the conjugate acid. So if we're looking to end with the conjugate acid, we can use our same thinking here. We go backwards. That means in this case, it's going to act as a base. Definition of a base is it will accept, right, an H plus. So in this case, we actually want to put the H plus on as we go this way. So we're going to gain an H plus, which will give us 2 hydrogens. CO3 -1 and +1 will equal 0, basically. Yeah. So we'll get carbonic acid basically there. Going the other way to our conjugate base, we want to end up the conjugate base. So just like we did before, we could deduce this going to act as an acid in this case. So it's going to give away an H plus in this case. And in this case, that would leave us a carbon, an oxygen, 3 of them. And it's already -1, gains 1 more negative. So we'll end up with carbonate in this case. Any questions on that? Once again, this guy and this guy are pairs. This guy and this guy are pairs. But going the double step there are not pairs. Again, the difference there being more than 1 H plus. Yep. Any questions on acid conjugate base pairs? Okay. So let's talk a little bit about acid strength. There are obviously, as we talked about earlier, weak acids and strong acids. Obviously, in this situation where we do have the arrows heading in both directions, is usually indicating that something is an acid, a weak acid, and a weak electrolyte. So as we talked about before, it will mainly stay together, but we'll be able to produce some H3O plus or H plus in solution. So it's still considered an acid, even though it's a weak acid, as opposed to something that maybe is a strong acid like up here, which will produce a lot of H plus or H3O plus in solution. So if the forward direction predominates, what you're going to end up with is really a strong acid, which is again 100% ionized or dissociated. Those are fancy ways of saying it. Basically 100% breaks apart into ions is basically what that means. So when it's floating in the solution, if you had something like HCl, which is a strong acid, you would have no HCl units still together. It would be 100% just H pluses floating around and Cl minuses floating around. None of them would stay together in the solution because it is a strong acid. A strong electrolyte will completely break apart, which is why it's considered a strong acid, because again, it's able to produce a lot of H plus very quickly in solution. If you have sort of the opposite direction, the reverse direction predominates, you're really going to end up with a weak acid, which, unlike a strong acid, will mainly stay together like this guy. So if you take something like HF, which is a weak acid, and you throw it into solution, you will mainly have HF still together in that solution as a unit, but it will produce a little bit of H plus and F minus. So again, because it's able to produce a little bit of that H plus, it's still considered an acid, but on comparison, it will not produce anywhere near the strong acid amount of H plus in that solution because it's mainly staying together. So it has a very hard time of frankly releasing that H plus into solution, so it doesn't produce as much. So how do you know if something is sort of a strong acid or a weak acid? There are a couple of ways you can know it, but let's talk first though about the relationship between sort of acid and bases and their conjugate partners. There's really an opposite relationship between them. And what I mean by that is if you have a strong acid, its conjugate base will be relatively weak. So sort of an opposite relationship. And if you have actually a strong base, its conjugate acid will be relatively weak as well. So anything that comes from a strong acid or strong base, its partner is relatively weak. And opposite is true if you have a weak acid, its conjugate base will be relatively strong. And if you have a weak base, its conjugate partner will also be relatively strong, which is the conjugate acid. Now, when we talk about in this sort of context here of the conjugate acid or conjugate base being strong, what it really is referring to is in solution, if you have one of these sort of conjugate acids or conjugate bases that came from a weak acid or weak base, it is relatively strong and it can actually continue to react with water. So for example, if we take HF, right, which is a weak acid, when it breaks apart in solution, it'll make H plus and F minus. And really the F minus here is its conjugate base in this case. And because this is a weak acid, this conjugate base will be relatively strong. Is it stronger than a strong base? It is not, but it is strong in the sense that it will continue on in solution. And because this is an aqueous solution, there's water there. It will continue on to react with water. And what it will react as a base, which means it will accept an H plus from water. And the result of that is we will end up with HF being made, some more of the acid. And more importantly, what will be made is actually hydroxide. So when we talk about sort of the conjugate acid or conjugate base being strong, it is strong in this sense that it could go through a reaction which is known as a hydrolysis reaction, which if you go on to 1B, we'll talk a bunch about that. But this hydrolysis reaction can basically change the acidity of a solution because the presence of this F minus will create more hydroxide, and more hydroxide would mean that this solution would actually end up being basic because there's a lot more OH minus being produced in this particular case. So again, when we talk about being sort of strong, it's not obviously stronger than a strong base or anything like that, but it's strong in the sense that it can continue to react with water and really have an effect on whether or not the solution is acidic or basic at that point. Any questions on that there? Okay, so how do we know if something is a strong acid or not? There is sort of a list of some strong acids which are really good to know for this class and future classes, especially 1B if you're continuing on that way. Hydrochloric acid is a strong acid. Hydrobromic acid is a strong acid. Hydroiodic acid is a strong acid. Perchloric acid is a strong acid. Nitric acid and sulfuric acid. So this list of like 6 or so acids are pretty much your basic core. These are strong acids. So like I said, it's really good to know as you continue on with chemistry, especially in this class and other classes, those 6. Because what you could do is, for the most part, if it's not one of those 6, you can probably make a pretty safe assumption that it's going to be a weak acid. So, some weak acids that commonly come across, HF, as I just wrote there, acetic acid that you guys used the other day, nitrous acid, HCN, and so forth. So these are some common weak acids. There's more, but like I said, if you kind of focus in on those 6 strong acids, again, probably a safe bet. If it's not one of those, it's a more of a weak acid that you're dealing with in that particular case. Strong bases are pretty easy to sort of find. Strong bases are usually those guys with hydroxide, so KOH, sodium hydroxide. And like I said before, if you go kind of the periodic table, group 1 and 2, somewhere around where sodium is, lithium is, come on down, hang a right there by calcium, and come down. Any of those guys with hydroxide is probably going to be a strong base. And as we saw before, obviously, there could be bases that are weak bases like NH3 that does not have hydroxide in it, but has the ability to produce hydroxide, which is how we know that it is a base. Any questions on that there? Now, we talked about diprotic and triprotic acids. There are some acids that are referred to as being oxyacids, and oxyacids are ones that contain oxygen, basically. So we've seen some before, like our friend nitric acid. And if you drew the Lewis structure for nitric acid really quickly, hoping for the best outcome here. We'll do that. There we go. So that's nitric acid right there, and it is this polar bond right there as to where that hydrogen comes off of. So that is the hydrogen that comes off as it donates its hydrogen in that particular case. There's a lot of organic acids that have a organic group that's known as a carboxyl group. A lot of those are weak acids. This is the carboxyl group here. And the one like you used the other day, acetic acid, which is really ethanoic acid, looks something like this if you draw it. And once again, it is the H here that comes off. That is the H that goes off to be donated as part of an acid. Any questions on that there? Now, sometimes when you look at an equation, sometimes people have, maybe not so hard in our class or necessary in our class, but in future classes, sometimes you want to know, are you dealing with maybe an acidic sort of situation or a basic situation? And one of the most simplest thing that you can see is in an equation on the product side, if you have either H plus or H3O plus that has been produced on the product side, it is probably an acid situation that's going on there. And if you look on the product side of the equation and you see hydroxide has been produced, it is probably a basic type situation that's going on there. So that is why sometimes it's really important as you go through chemistry classes to be able to properly write equations, because it can give you a lot of information. Having taught, for example, 1B a lot, that is what gives students a really hard time is they don't know how to write an equation. And it can be so much helpful to you as you try to do the math part of the problem. If you have the equation in front of you correct, you can understand, oh, this is like an acidic situation or this is a basic situation. So, it's really important, at this stage, obviously, to make sure you know how to write equations properly. But as you continue on, it could actually make the calculation part of the class a lot easier as well. Any questions on that there? So as we mentioned before, water, which is an amphoteric substance, can act as an acid or a base, can actually react with itself. We saw both reactions here. In this case, the water is donating, so it's acting as an acid. And in this case, the water is accepting that H plus, so it's acting as a base. In the case of water reacting with water, which is the autoionization of water, one is the acid, one is the base. And that is basically what is happening in water all the time. So you have a certain level of H plus and OH minus basically floating around in there. That's why when we talk about H plus and OH minus, that makes water. That's basically where it comes from. And it's what happens in a water environment all the time. They're reacting with each other along with other stuff that you might dump in there. And whether or not your water is acidic, basic, or neutral, it has to do with sort of the levels of H plus versus OH minus in that solution. One of the relationships of that autoionization of water is it creates an equilibrium. And we could have an equilibrium constant, which is known as Kw in this case. That is really the ionization constant of water. It is really what is referred to as an equilibrium constant. And what equilibrium means, at some point, this is a reversible reaction heading in both directions. At some point, the rate of the forward direction will equal the rate of the reverse direction. So it's going back and forth at the exact same rate, which means it locks everybody into place. Equilibrium doesn't mean that you have equal amounts on both sides. It actually is referring to the rate of how fast the reaction's happening in both directions. And when it reaches the equal rate, what that does is it locks everybody into place. So whatever the concentration of reactants are at that point, they basically stay, and whatever your concentration of your products are at that point, they stay at that level. And we have this relationship here, which is Kw, that the concentration of H3O plus times the concentration of OH minus equals 1 times 10 to the minus 14. The brackets mean concentration, and what they usually refer to as molarity, which is moles per liter. So that's usually what the little brackets mean. I personally will write Kw like this. Kw is the H plus concentration times the OH minus concentration, and it equals 1 times 10 to the minus 14. That is pretty much a constant number. The reality and the truthful answer is it does change with temperature, but pretty much if you need to use Kw, that is usually the number most people will use under normal conditions. The H plus is really the acid part of the solution. The OH minus is the base part of the solution. So we could actually use this to solve for one or the other. The calculation is exactly the same. The H plus equals 1 times 10 to the minus 14 divided by the OH minus concentration, and vice versa. The OH minus concentration is 1 times 10 to the minus 14 divided by the H plus concentration. It is really important in this chapter to make sure that you use your exponent button. Yeah, so there's a lot of numbers and scientific notation that you need to do. So a reminder, hopefully you still remember and are doing this, but make sure that you definitely punch these things in with the exponent button, because we're going to start using logs and some other things as well. So if that's how you're doing scientific notation, which is incorrect, you're going to be in some trouble in this chapter for sure. So make sure, definitely use those exponent buttons when you punch these things in. So we could actually compare those two concentrations and determine whether or not the solution is acidic, basic, or neutral. If we compare the H plus concentration and it is larger than the OH minus concentration, basically the acid part is larger than the base part, the solution will be acidic. If the OH minus concentration is larger than the H plus concentration, really the basic part is larger than the acidic part, it will be basic. And if they are equal to each other, that means they both will have a concentration of 1 times 10 to the minus 7. That will give you a neutral solution. All right, so why don't we try some here? So for each of these 4 separate problems here, calculate the OH minus or H plus, and why don't you determine so in this case we're given the H plus concentration. So in each of these problems here we could use Kw, which is our H plus, times our OH minus, which equals 1 times 10 to the minus 14. Like I said before, good news is it doesn't matter which one they give you, really it's the same calculation. So in this case we're going to be looking for our OH minus concentration will be 1 times 10 to the minus 14 divided by the H plus concentration. So putting our numbers in, we get 1 times 10 to the minus 14 divided by 3.4 times 10 to the minus 4. Once again, we want to make sure that we use our exponent button. 1 exponent minus 14 divided by 3.4 to the minus 4. And that's going to give us a 2.9 times 10 to the minus 11 molar in this case. The molarity would be the same as the original concentration. Any questions first off on that calculation? A reminder that if this part of the number is good, but this part, the exponent part's off, is probably the way you're punching it into your calculator. This would be acidic, basic, or neutral. We want to compare the H plus concentration to the OH minus, which one's larger? It is the H plus concentration. This is the OH minus, which is to the minus 11. And this is the H plus, which is to the minus 4. A reminder that the negative there is important. It's actually the smaller negative number is the larger. That is because if you take 3.4 times 10 to the minus 4, you're going to go 4 places this way and put zeros. If you take 2.9 times 10 to the minus 11, you're going 11 places this way and putting zeros, which makes it a much smaller number. So negative exponent, smaller number, smaller negative exponent is the larger number. So this would be acidic in this case. Any questions on that? Coming to our next one, basically same calculation. We're going to do a little OH minus is equal to 1 times 10 to the minus 14 divided by our H plus. And in this case here, 1 to the negative 14 divided by 2.6 to the negative 8, going to give us, looks like 3.8 times 10 to the something, 7, 6, 7, minus 7 molar. Once again, we're going to compare the H plus to the OH minus, and really all you have to compare is these exponents. And in this case, this guy is the smaller negative number, which means it's actually larger. So the OH minus in this case is going to be larger, and that would mean that this is basic. Any question on those two there? All right, continuing on to the next two that we have some OH minus concentrations given to us. So we have in this case OH minus equals 6.2 to the minus 9, 6.2 times 10 to the minus 9, and 8.1 times 10 to the minus 3. So once again, we're going to use our KW here. So in this case, we're solving for the H plus. Our constant value of 1 times 10 to the minus 14 divided by 6.2 times 10 to the minus 9, going to get us it's like 1.6 times 10 minus 6 molar. In this case, it is going to be the H plus is larger than the OH minus. Again, to the minus 6 is larger to the minus 9. And again, this would be acidic. And here we have our H plus would equal 1 times 10 to the minus 14 divided by 8.1 times 10 to the minus 3. That gives us, looks like 1.2 times 10 to the minus 12 molar. And in this case, minus 12 is much smaller than the minus 3. So it is the OH minus that is larger in this case, which means it should be basic. Any question on any of those calculations? By the way, just a reminder that the relationship between H plus and OH minus are opposites. So as the concentration of H plus increases, the concentration of OH minus decreases and vice versa. So really as one goes up, the other goes down. And that is constantly sort of happening. And that's how we get either an acidic solution or basic solution. The less H plus we have, the more OH minus we have in the solution, which makes it basic. And the more H plus we have, the less OH minus we have in the solution, makes it acidic. Any questions on any of those there? All right, let's try one more here to make sure we'll forget this part. Let's just calculate the OH minus concentration. And is it acidic, basic, or neutral in this case? And the minus 14 divided by our H plus concentration in this case. Looks like 3.6 to the minus 10 in this case. Again, it would be molar. And comparing our acid part, which is -5, to our base part, which is -10. That means here the H plus is greater than the OH minus, and this would be acidic in this case. Any questions on KW, H plus, OH minus? Okay, the next thing we're going to talk about then is we're going to skip this example and we're going to talk about the pH scale, which is important. So the pH scale is a measure of acidity of a solution. It measures, like it says, pH, the amount of free H plus there are in solution. The pH scale runs from 0 to 7 to 14. Below 7 is acidic. Above 7 is basic. And really, like I said there, dead on 7 is neutral. And that's what we're going to use in this class, that dead on 7 is neutral. If it's a little bit above 7, then it's slightly basic. If it's a little below 7, it is slightly acidic. And that's really because, as we saw in the previous slide, H plus would equal the OH minus at that point. So they actually would have equal concentrations, which means you actually should have a pH of 7. 7 is sort of your center point. As you go from 7 towards 14, you're becoming more basic. As you go from 7 towards 0, you're becoming more acidic in this particular case. To calculate the pH, we will use the equation here, which is the pH is equal to minus the log of the H plus concentration. This is also one where you could substitute in minus the log of the H3O plus concentration. And again, a lot of books will probably use the H3O plus. Again, same thing. It doesn't really matter which one that you want to use in this case. Let's talk a little bit about calculations. We did talk about calculators. If you have a display calculator, this formula and all the rest of them we're going to talk about, you basically should put it in exactly the way it's written. Hit the negative button, not the subtract button. You want to hit the log button, and then you want to put your number in scientific notation. If you have a non-display calculator, you want to actually start with the number. You then want to hit the log button, and then you want to use the negative button, not the subtract button, to change it. If you're not sure what type of calculator you have, hit log. If it says log, congratulations, you have a display calculator. If you hit log and it says error, congratulations, you have a non-display calculator. That's how you determine the difference there. So with all this formula and all the rest of them, depending on your calculator, you got to put it in one way or the other. But you definitely still need to make sure you use your exponent button as well when you do put those numbers in. So you need the H plus concentration to calculate the pH, and you should probably always go by the pH value as to determine whether or not the solution is acidic, basic, or neutral if you have it, because the pH scale is what most people have in their head. And as we'll talk about in this chapter as well, there is really only one answer to that question. Is it acidic, basic, or neutral? You cannot have both an acidic and basic solution at the same time. Although on exams, sometimes people write that the same solution is acidic and basic at the same time. I've never had anybody write all three. It's acidic, basic, or neutral, but they do write sometimes acidic and basic. And we'll talk about why that happens in certain cases. But let's talk about significant figures when we do calculate something like pH. The number of decimal places in your pH answer should be the same number of significant figures there are in the concentration. So we're going from sig figs to decimal places. So if you look at the concentration you're using to calculate the pH, however many significant figures there are in it is how many decimal places, not significant figures in your pH, but how many decimal places in your pH. And we're going to talk about going backwards from pH to concentration. Works the same way. If you have a pH value that has a certain number of decimal places, that is how many significant figures your concentration should have. So let's just try one to make sure here. What is the pH of a solution that is 1 times 10 to the minus 5? So punch that into your calculator, depending on which type of calculator you got going on. Okay, so we're obviously using this equation, pH equal to minus the log of the H plus concentration, which means it will be minus the log of 1 times 10 to the minus 5, depending on your calculator. If you have a display calculator, you should hit the negative button, you should hit the log button, you should hit 1, the exponent button, the negative button, and 5, and hit equals. If you have a non-display calculator, you should hit the 1, the exponent button, the negative button, and 5, then hit the log button, and then hit the negative button. So whichever way you got going on there. When you do all of those anyways, you should hopefully end up with a 5. I hope, staring at you at the screen. Yeah. So 5 is the pH of the solution, but how should we report it? Should we report it as 5, 5.0, 5.00, 5.0000000? That feels like a lot of zeros, so we'll just eliminate that one. So what should be the proper reporting of this pH value? So the rule says that the number of significant figures in our concentration, which is this one, and this is a number written in scientific notation, which means all the numbers that come before the times 10 part are significant. This guy would have 2 significant figures, which translates to 2 decimal places, not sig figs, but 2 decimal places. So the correct way to report this answer would actually be this guy. That doesn't have the right number of decimal places, and this one does not have the right number of decimal places. So once again, it is 2 significant figures to 2 decimal places is what we're looking at when we go to report it. Question on that there. By the way, this would be acidic, basic, or neutral. Would be acidic, as it is less than 7. Yeah. Any questions on that there? All right. Yeah. Yeah, technically speaking, we're going to go with that in this class. Some people will not and stuff. So the truthfully is 7.00 or so really is neutral. And that's because, as we saw on the earlier slide, the H plus concentration equals the OH minus concentration, which means they both will have a value of 1 times 10 to the minus 7, which if you then put it into your pH, minus the log of 1 times 10 to the minus 7 is a pH of 7 on the nose. So technically speaking, 7 on the nose is neutral. And just so there's no misunderstanding, that's what we're going to go with in this class as well. If it's a little bit above, like 7.1 or something like that, it is going to be slightly basic. If it's like 6.9, it's going to be slightly acidic. There are some people that'll say, hey, there's a little area on both sides that is still technically neutral. So there's no misunderstanding. We're just going to cut it off straight at 7 for us, but it's going to be neutral. Other questions on that? Okay.